Hello everyone. My name is Maozhong Fu. I will be presenting our paper titled Sparse Modeling of the Early Part of Noisy Room Impulse Responses with Sparse Bayesian Learning. Let's get started. My presentation includes 4 parts. Firstly, I would like to give a brief introduction to the problem we are trying to deal with. A room impulse response mainly consists of 3 parts, which are direct sound, early reflections, and late reflections. It can be noted that the early part, which includes direct sound and early reflections, is relatively sparse. Modeling of the early part of RIRs see many applications, such as room geometry reconstruction, augmented and virtual reality, and dereverberation. RIRs typically are modeled as long finite impulse response filters, which may have thousands of coefficients. Some L1 regularization-based approaches utilize the sparsity of the early part of RIRs to reduce the coefficient number. However, they are sensitive to regularization parameters. One common way to find an optimal regularization parameter is using grid search, but it is computational heavy in practice. Another common way is to use cross-validation, but it requires suitable training data which may not always be available. Sparse Bayesian learning has been proven that it is insensitive to the user parameters. The hyperparameters of SBL are learned adaptively from data. And SBL is quite computational efficient and sparse promoting. Therefore, we propose to use SBL to model the early part of RIRs. Next, I'm gonna introduce some details of the proposed method. After discretizing the RIR measurements in the time delay domain, the measurements can be expressed as the sum of the noise and the convolution result between the model coefficients and the source signal. Then we can convert it into matrix form. The model coefficients can be represented by a vector x. In a typical scene, the early part of an RIR contains very few impulse responses, thus x is mostly zeros. Based on the signal and scene models, the modeling of RIRs can be converted into solving 2 problems. Problem 1 is that given y, how to recover x with the a priori that x is sparse. And problem 2 is that if the source signal is unknown, how to determine phi. We deal with problem 1 with SBL. SBL adopts the assumption of the prior that the MTH component of x follows a zero-mean Gaussian distribution with variance gamma m. So when gamma m gets close to 0, xm approximates to 0 with probability 1. SBL also assumes that the noise follows a zero-mean Gaussian distribution with variance lambda, which affects the likelihood. In the framework of SBL, given lambda and gamma, the posterior can be determined by the Bayes theorem, thus the maximum posterior estimation of x can be obtained. After maximizing the marginal likelihood, estimators of lambda and gamma can be obtained. After carrying out enough iterations, the most of gamma gets close to 0, which makes most of x become 0 indirectly. To deal with the second problem, we assume the source signal is a Gaussian modulated pulse, which is widely used for bandwidth-limited signals. And a Gaussian modulated pulse is controlled by 2 parameters. We also assume the direct sound has the highest amplitude in the measurements. Based on the 2 assumptions, we use a rectangle window to extract the direct sound. Then, the parameters of the Gaussian modulated pulse can be estimated by minimizing the mean square error between the measured and reconstructed direct sound. With the estimated parameters, the dictionary can be built with the various time-delayed source signal. Then, I'm gonna show the effectiveness of the proposed method with simulation and experiment results. Observe the recovered RIRs by the proposed RIR-SBL and the lasso-based method lasso-RIR. It can be clearly seen that the proposed method is more sparse around 3 to 7 milliseconds. We also show the histograms of the reconstructed RIR measurements. It can be noted that the proposed method has more coefficients around 0, which means the proposed method is more sparsity promoting. To show the effectiveness of the proposed method in noisy conditions, we compare the output SNR between the proposed method and the lasso-based method. We can see the proposed method has a higher SNR gain than the lasso-based method. Also, we compare the time cost between the proposed method and the lasso-based method. Due to the fast convergence of SBL, the proposed method has much less time cost than the lasso-based method. In real-world data processing, the proposed method also shows higher performance in sparsity promoting than the lasso-based method. it can be seen that the proposed method can greatly reduce the noise. The same conclusion can be drawn from the histogram of the recovered real-world RIR measurement. Finally, I would like to give a summary of the proposed method. The proposed RIR-SBL works well in noisy conditions and can improve the output SNR. And RIR-SBL is computationally efficient due to its fast convergence. It has been shown that RIR-SBL can effectively exploit the sparse structure of the early part of RIRs to promote the sparsity of the model. Thank you for your time.